Thank you very much for that introduction and correct pronunciation of my name. So I'm going to start by giving really an overview talk on carbon cycle feedbacks, permafrost, and overshoot warming. And if you've been with us all day, you will recognize a lot of this material from an earlier session. But I'm also giving some more perspectives on overshoot warming and the whole concept of what that is and what it means for permafrost. So I'm going to show you a lot of material that's from the latest report released by the IPCC. So Working Group 1 report from the 6th assessment report. And in general, you just find all of the references to the, either to the papers or to relevant figures in the report in the bottom left if you want to learn more about the material I'm showing, because this is just really an overview. This is from the summary for policymakers, and it's a figure that shows cumulative human emissions on the x-axis plotted against global warming on the y-axis. And basically what you see here is that there's a really almost perfect linear relationship between how much CO2 we've emitted and how much global warming we've seen. So this tells us that really every ton of CO2 released adds to global warming. Another important message from this graph is actually that it could be even worse, and that is because the Earth system is actually absorbing roughly half of the emissions that humans are putting out, either in the terrestrial biosphere or in the ocean biosphere. This line illustrates how the warming roughly would actually look if we didn't have the biosphere taking up so much of the CO2. It would be a lot worse, and it would be really an accelerating warming trend rather than a linear one. Unfortunately, we see that these natural Earth system sinks, they are weakening, and they will be progressively weakening even more with higher emission scenarios. This is another figure from the IPCC report that shows the bars show the cumulative human emissions in different scenarios, ranging from a low emission scenario in blue to the left to a very high emission scenario in red to the right. And then you see, the total portion that ends in the atmosphere is this gray upper bar, and then you see you see the chunks of those emissions that are actually going to be reabsorbed into the Earth system, and thus cooling the climate, or not cooling, but limiting the warming, the ocean or the land. And what we see is that in the low emission scenario, the Earth is going to be doing us the favor, actually absorbing 70% of our emissions. But if you go to the high emission scenarios, these sinks really saturate, and only 38% of the human emissions can actually be absorbed back into the system. I'm going to get back a little. So I'm going to get back to part of the mechanisms of why that is in a while. Also here, I want to highlight a few of the take-home messages that the IPCC listed on carbon cycle feedbacks in the summary for policymakers. They find that carbon climate feedbacks, so Earth system feedbacks that actually warm the climate even more in a feedback loop that makes global warming worse, they increase with warming, and they become more uncertain with warming. So our ability to project these feedbacks actually becomes smaller and smaller, the higher the warming is, basically because of unexpected or behavior in the Earth system, and also because we are moving the Earth so far out of the envelope of where it's been before, that it becomes more increasingly difficult to actually model these processes. But with that said, the IPCC also find that the different scenarios, the human emission scenarios, the SSPs, still dominate uncertainty in the magnitude of future atmospheric CO2 concentration. So most of the uncertainty still comes from the human behavior, as opposed to our imperfect understanding of the carbon cycle feedbacks. Another important point is that some really large carbon cycle feedbacks are not included to the CMIP6 or the AR6 models. And this will cause even higher CO2 and methane emissions than what we see in most of the graphs and so on. And the key ones are wetlands, permafrost thaw, and wildfires. And I'm going to zoom in more on the permafrost thaw aspect of it soon. We've heard about wetlands and fires in earlier sessions today as well. This graph shows you the carbon cycle climate feedbacks that are in the models. I just talked about the ones that aren't, but many of the processes are, of course, included in it. I mean, the models are dynamic; they have vegetation changing with emissions, etc. And this is another figure from the IPCC report that breaks this, the most important feedbacks into a couple of different categories. The two top ones that are blue graphs, they are the land and the ocean carbon response to elevated CO2 in the atmosphere, which is actually a really strong cooling feedback. So the more CO2 we put in the atmosphere, the more productive plants are, and the more rapid the exchange between the atmosphere and the sea surfaces. So basically, carbon dioxide has been taken up by ocean, causing ocean acidification. But these feedbacks are still cooling the climate quite a lot. On the lower two lines, you have land carbon and ocean carbon response to climate. So the first, the cooling feedback is response to more CO2 in the atmosphere. The warming feedbacks we see here, they are responses to the actual warming of the climate. That anything as soon as temperature increases, chemical reactions are speeding up, and you actually see a more rapid degradation of carbon stored in soils, or an acceleration of the ocean carbon climate cycle, which leads to these positive feedbacks. And if we go to a graph of the global carbon cycle, here you see there are a lot of arrows showing the sort of natural state of the carbon cycle, more or less. And there you see the numbers of fluxes or of pools in yellow and blue text. I'm not going to go through all of them, but we see that these are all very big numbers. The unit here is gigatons of carbon. So if you want to convert it to gigatons of CO2, you have to multiply it by 3.7. So if you don't recognize the numbers, that's because of the mismatch in units. But what I want to focus in on here is the red numbers. You see the human emissions in the middle there, 9 petagrams of carbon per year, roughly equivalent to 33, 34, 35 petagrams of CO2, depending on which of recent years we're talking about. But then you also see in the uppermost left corner, you see 120 plus 3, if you can read that. And the plus 3 there is actually the cooling carbon cycle feedback of increased photosynthesis due to CO2 fertilization. And you have a 90 plus 2 when it comes to air-sea gas exchange, which is, again, this cooling feedback that even more CO2 is being taken up by the ocean due to human emissions. So those red numbers also show human perturbation to the climate system. And this next graph, again from the IPCC, shows us carbon cycle climate feedbacks that are missing in the Earth system models. I already talked a little bit about this. And here we see that the IPCC report actually quantified these, even if they're not in the models. They used, meta-analysis of existing literature and actually calculated roughly the size of these feedbacks. So you have fire response to climate, permafrost response to climate when it comes to both CO2 and methane, and then the wetland methane response to climate. You see, these are all positive feedbacks. These are all warming the climate further. And if we add them all together, they equal roughly 5 to 10% of total human change in radiative forcing. So it's quite a significant additional feedback on top of other, on top of the more direct forcing from emissions. And by far the biggest one is permafrost response to climate. The methane response might actually be a little bit underestimated here still, but it's really progress that the IPCC have quantified these feedbacks, and they're also accounting for them in projections of remaining carbon budgets to stay under certain climate targets. Okay, but zooming in a little bit on permafrost. The session is about permafrost thaw and overshoot. The permafrost thaw is a warming feedback. You have a very large area of permafrost in the northern hemisphere. Roughly 20% of all of the land surface in the northern hemisphere is affected by permafrost. So you have several million square kilometers. And as global warming thaws permafrost, there are enormous amounts of carbon that's been locked into permafrost usually for thousands of years, that can be accessible to microbes as temperatures warm, and the microbes start to degrade this, and they produce methane and CO2 as byproducts. The permafrost region stores more carbon than the whole atmosphere and all plants living on Earth combined. So it's really it's a problem, or it's processes of a massive scale, and it's also processes that act over a very long time scale. So it's a system that's relatively slow to respond to climate warming, but once it starts to respond, the response is almost inevitable on policy relevant timescales. And this becomes especially important when you get into the topic of overshoot warming. So what is overshoot warming? I've tried to illustrate that here in this simple conceptual graph where you have time on the x-axis and temperature increase on the y-axis. And the black dotted line represents the target temperature. Let's call it 1.5 degrees if we're optimistic. And then you have basically two ways of getting there. You have the really nice way in the green line, which is rapid emission reductions to just reach the target temperature and stabilize. And then you have the other option where you actually overshoot the target temperature, keep emitting fossil fuels for a few more years to buy yourself time to sort of restructure your economy or whatever reason you have for wanting to keep emitting. And then you rely on negative emissions technologies later on to pull those emissions back down into the atmosphere, and you get an overshoot warming that goes above 1.5, perhaps up to 2, and then down again. And the problem is that a lot of the Earth system feedbacks are going to be triggered by this overshoot warming, and some of them may not be reversible. So if we add permafrost to this, the first problem is that the permafrost drives further warming that might be even stronger. So you actually get an even higher overshoot than what you had initially planned. And the second problem is that to a large extent, there's going to be irreversible permafrost loss. Permafrost doesn't grow back very easily, at least not all sorts of permafrost. And the permafrost thaw also triggers carbon loss that persists for centuries. So you're sort of you're triggering a problem that doesn't back down when the climate backs down, essentially committing several future generations to have to deal with these increased emissions for centuries. And the key aspect here is that permafrost is not just organic material or soil. A lot of it is massive ice in the ground. And this has been built. There are a lot of different types of massive ice, and there's a whole scientific discipline dedicated to the study of permafrost ice and its ice bodies. But the common denominator of most of this massive ice is that it takes a really long time to build up. And when we thaw it, perhaps during this overshoot time, the ice melts, it drains away, you get collapse of the whole ground surface. And also, even if the climate is brought back down, the ice is not going to regrow anytime soon. That will take centuries or millennia. So the permafrost thaw that is triggered in this way will keep emitting carbon in these thermokarst or abrupt thaw landforms for a very long time. And we see this happening already. It's observed. This is from scientific papers observing this in very cold parts of the Canadian Arctic that should still be frozen at least for another 70 years, according to models. But it's already happened. And this is a response where you see massive abrupt thaw really changing the whole landscape in response to a few summers of regional heat waves in the Canadian Arctic that happened a few years ago. And in the last few summers, from news reporting that there's been even more extensive heat waves across all of the Arctic, which in turn has certainly triggered even more massive thaw that is making the situation worse. And this is a slide that shows observed permafrost extent with a combination of remotely, so using satellite temperatures and the state-of-the-art model. And that was 2003, 2010, 2017. So if we go back and forth, you see very rapid loss of the near-surface permafrost over just a few decades. I want to emphasize that in a lot of these areas where the permafrost disappeared, you might have deeper permafrost still there, but this is really the near-surface permafrost that is being thawed rapidly. And this is also happening more quickly than what models had projected for this time period. So the IPCC also asked the questions, which is very relevant to overshoot warming then, is could climate change be reversed by removing carbon dioxide from the atmosphere? And you see, their conceptual overshoot warming scenario there, where you have a very pronounced CO2 peak, and it goes back down, and it stabilizes around 400 ppm in this example. And their answer to this question, it varies depending on what part of the climate system you're talking about. You can reverse it if you're talking about global surface temperature. there's a lag time of a few years, but then models project that temperatures would stabilize if we could use negative emissions and draw them down. Other Earth system components have lag times of decades to centuries. Here they project that the permafrost area will stabilize after a few decades, but note that it's stabilizing at a much lower level. And yet other Earth system components, they don't stabilize at all. Well, they might in a very, very long time. But here you see, millennia, centuries of ocean thermal expansion just keeps going. Over there, and you have ocean acidification is another example of processes that move over extremely long time scales. So you can't just flip them around and back them up again. Ice sheets are the same. Once you trigger those dynamics, it's really hard to back down from it. I'm going to go back to the permafrost example again. And here the IPCC says yes, but decades of lag time. But in reality, these huge areas of permafrost that we already lost, they are going to keep emitting permafrost carbon for centuries. So there's a lag time of decades in the area, but there's a century scale lag time in the actual emissions, because you have already lost several million square kilometers here, and they are irreversibly lost in this scenario. So what does this mean then for sort of estimates of remaining carbon budgets? For the first time, well, not for the first time, but in a more detailed way, the IPCC have actually included permafrost carbon in these numbers, which is really nice. Now I just moved it from the gigatons of CO2 remaining to us to years remaining to us if we think about emissions equal to last year. So you have 1.5 degrees warming, 1.7 degrees warming, 2 degrees warming, and different sort of levels of chance to reach that target. And if we want to be on the safe side and say have an 83% chance of landing at a certain target temperature, we have 9 years still of emissions to reach the 1.5 degree target, almost 30 years to reach the 2 degree target. Unfortunately, there are processes that we are becoming to understand that might point to this even being optimistic. You will hear more about this in later talks. Unfortunately, we're in a situation where we see that carbon dioxide emissions from human sources have rebounded from the COVID-19 pandemic. This is a figure from a non-reviewed preprint of a scientific paper. You see the reference at the bottom. And it just shows the projected emissions going to the end of this year. So this projection puts 2021 just 1% lower than 2029. So than the highest pre-pandemic emission year that we've had on record. So we still might be 1% lower, which means that we actually still have a chance to say that 2019 was actually peak carbon, was the year where we had the highest emissions, and we still have a chance to actually go. If we go down again, 2022, perhaps peak carbon has passed. Perhaps it hasn't. We'll see what this conference and other efforts where they get us. Okay, so to summarize, we see that the natural carbon sinks in the Earth system are weakening. This differs with different scenarios. The CMIP6 Earth system models, so that's the ensemble of models used for the last IPCC report, they lack some really important long-term feedbacks, including permafrost. But they do, in the report, quantify these missing feedbacks and accounted for them in the remaining carbon budgets. That give us about 8 to 9 years to stay below 1.5 degrees if we stay at the path we're on. And the IPCC also conclude that CO2 removal can rapidly limit global surface warming, but other Earth system components will lag anything from decades to millennia, and that includes permafrost, most certainly. And another important message to also bring to the next coming talks in this session is that overshoot warming, if it happens, will trigger irreversible permafrost thaw that will drive additional warming for centuries even after the climate stabilizes.